Okay, welcome back. This is the second video on modular functions. We're starting with something that we left off with last time, the Weierstrass elliptic function, P of z, and last time we kind of derived it. We came up with something that looked like this. This sum here is over all the lattice points. You can see this is omega, all these lattice points, and this would extend all over the complex plane. And how did we get here again? Well, we looked at what an elliptic function could be. We found out by definition, I should say, the elliptic function is doubly periodic with two periods, omega 1 and omega 2, that are complex, and their ratio is not real. We also had that it was meromorphic. We found that it could either be constant or non-constant. And in the case that it's non-constant, it has to have the same number of poles as zeros. And further on this poles thing, if we integrate around one of these parallelograms, if we integrate the function, the elliptic function f, around one of these parallelograms, we find that the integral around the parallelogram is 0, which means the sum of the residues, at the poles is 0, which implies that there's at least two simple poles, or at least one pole of order 2 or greater, okay? And so what we did was the pole of order 2, the double pole, is the way that Weierstrass went. The two simple poles is the way that Jacobi went. And all we're doing here is we're trying to find the simplest elliptic function that we can think of. So we started looking at something like this. I'm not going to fill in the indices. I'm just going to show you where this is basically we have a double pole at every point on the lattice. Okay? And we found out that this series actually does not converge. So we took this series, which was the smallest integer for which this series converges, and we integrated it from 0 to z, and that gave us a constant times p of z. So that's how we got here. The next thing that we'll talk about is this Laurent series expansion at z equals 0. This is a natural thing to investigate, since we're really just interested in what's happening in maybe one of these parallelograms, as it's going to translate to everywhere else in the complex plane. So I'll just say that again. Whatever's happening in here is the same thing that's happening here and here and here and all of that, right? Because we have a doubly periodic function. So it makes sense to check out the Laurent series around z equals 0. And we can find this just by recognizing that, that this right here is pretty close to a derivative of this geometric series, which we can actually consolidate into something that looks like this. Then we kind of expand that, collect our terms, and recognize that p of z is an even function, so we should only have even integers for our exponents there. And then g here, these are Eisenstein series. So they look like this. These are the series that Eisenstein investigated in the 1800s, that he found some interesting algebraic relationships between. So here you go. Here's our Laurent series. What I'm going to do now is I'm going to expand this a little bit. I'm going to show you some interesting arithmetic. This is where it really starts to get pretty beautiful. Okay, so before we start with this, what we're going to do is we're going to show this very interesting differential equation. I'll just read this out. The derivative of p of z squared equals 4 times p of z cubed minus 60 g4 p of z minus 140 g6. Now the goal here is going to be manipulating poles. If you'll remember, elliptic functions either have poles or they don't. If they don't have poles, they're constant. So if I can algebraically manipulate this, or this series in some way, or this series in some way, so that I can cancel out all the poles, what I'm left with is an elliptic function that doesn't have any poles. An elliptic function that doesn't have any poles is constant. So that's exactly what we're going to start doing here. Here I've expanded this. This is P of z. Keep in mind, this is the only thing in this series that looks like it can give me a pole. Remember, a pole is just a singularity, like a removable singularity type thing. So here we have 1 over 2z. Well, obviously, when z is 0, that's going to give me a pole. Everything else here looks pretty entire to me. Over here, I've got p prime of z. Now, this is going to be the only thing that can give me a pole in this series, right? The rest of this looks like a polynomial. It's not going to give me any trouble, I don't think. So let's start doing this. I'm first going to expand this series, and then I'm going to give you pz cubed, and we're going to try to do some algebra and get rid of these poles. Okay, so again, this is what we're aiming for, this differential equation right here. I've gone ahead and expanded some of these things so that hopefully our algebra is pretty neat. What we do is we start with p prime of z, and you can see that this is an odd function. Look at all the exponents of z here. That's an odd function. I can't do much with that in terms of an even function. So I'm going to square it, and I'm going to get back to an even function. Okay, and you can see all of the exponents of z here are even. So we start with p prime z squared. Then I'm going to subtract 4 copies of p of z cubed. All I did was I multiplied these series by themselves. Okay, now here we go. This is going to kill off the 1 over z sixth term, right? But it's going to leave us with some stuff. Here we have minus 24g4 over z squared. And here we have 36g4, which we're subtracting from 24g4. So here we have minus 60 g4 over z squared. Here we have minus 80g6. We're subtracting 4 times 15 of g6. So that's going to be 80g6 minus 4 times 15 is 60g6. So 80 minus 60 is minus 140 g6. And I went ahead and I expanded it one extra term because I want to show you something really cool here in a second. This is kind of a pain in the nuggets, but I think you'll appreciate it. What I'm going to do, though, is I'm going to write what 4 times each one of these coefficients is so I don't make some stupid mistake, which now that I've said it, I'll probably do anyway. Remember that we're subtracting these things, so 36 minus 108, that's going to be minus 72 g4 squared. And 168 minus 81, minus 168 minus 81, what is that? That's going to be minus 279, is that right? Minus 279 G8. I feel like I'm making an error. Oh, yeah, that's because that's wrong. 4 times 21 is not 81, you dope. Okay, hang on here. I'm actually going to pause this for a second. Just make sure that I'm doing my math right. Okay, well, I double-checked my math, and boy, was I wrong. So this is why you got to be careful, ladies and gentlemen. This was some dumb, dopey stuff here. I actually did more than 100 there for some reason. Anyway, this is the danger of doing arithmetic without double-checking yourself. This is what it should be. So 168 minus 84 is minus 252. And here's our coefficient for our z-squared term. Now, if I'd been doing this with just the normal number of terms, just trying to kill my poles, I would not have made that error. But I'm trying to show you something really cool here in a second. So anyway, here's what we have. We've got this term here. Now, both of these are elliptic functions. What do we need to get rid of? Well, there's only one pole here, and it's right here. Okay. So what it's going to take is we're going to need to add 60g4 times this original one, right? Because we've got a 1 over z squared in p of z. So we're going to add in 60g4 p of z. And what's that going to give us? Well, it's going to kill this term. That's great. There's no constant term here, so I'm going to be left with minus 140g, excuse me. And then I'm going to need to add 3g4 times 60g4, which is going to be a total of, so that's going to give me 180g4 squared, okay? So I'm adding that to this, and 180g4 squared, 180, oh my god, 180g4 squared. I should make excuses for myself, but I don't even feel like it. Okay, here you go. 180g4 squared, we're going to be adding to this 72. Now that's clearly plus 108g4 squared, okay? And then we don't have anything here. We've got nothing to subtract from this odd-looking g8 term. Okay, and that's all this stuff is order 4 or higher. So look at this for a second, though. Here we've done algebraic manipulations on an elliptic function. So this side is elliptic. This is equal to this, and it's elliptic, so this side is elliptic. But this doesn't have any poles. So what does that mean? That means this doesn't have any poles. Well, that means they're both constant. And further, since this is the only term that's constant in this whole series or whole jumbled mess, that means that all of these things are 0. So this gives us the differential equation we initially started out to find. P cubed, that's a 3, minus 60g4p minus 140 g6. This gives us this differential equation. Since this is the only thing that's constant, we're just scooting all of this stuff over to the other side. But look what it also says. It also says that this term has to be 0. In other words, 108g4 squared minus 252g8 has to be 0. In other words, 108 times this funky series equals 252 of this funky series. That's weird, right? Not only that, you can see that there's going to be infinitely many terms here. And all of those terms get increasingly complex. And if you have the patience to go through and double check yourself, which, I'm not even sure that this is accurate just because I'm liable to make some kind of numerical mistake, but rest assured, there is some funky relationship like this for every single one of these terms that comes in front of an even power of z. That's weird. Okay, we're going to talk a little bit more about this, and then we're going to move straight into the modular function. The first modular function, that we'll speak about. Okay, the next thing that I'm going to talk about, and then I'm going to skip a section, is these invariants. Maybe you noticed these kind of funky looking coefficients in this differential equation. Well, there's other differential equations that look just like this. And you can actually do a lot of things just by manipulating this function and this function. When I say this and this, I mean the derivative of the p-function and the p-function itself. It turns out that you can actually make any elliptic function out of a rational function of this and this. Okay, all you have to do is kind of what we just did, where you account for the poles, and eventually you're going to come to something that's constant, and you're done. You'll see that in the exercise video, listen to me, if you have that much patience or give that much of a shit, but there you go. The other thing is these invariants G2, which you see here, and G3, which you see here, actually spawn all the rest of the Eisenstein series. In other words, Gn can be written as a polynomial of G2 and G3 for all n. Okay? So we really only need to look at these two things. Now the next thing I'm going to say, and then I'm going to drop it for a second, I'm going to show you what these things actually look like in practice, is that there's also a discriminant to this equation here. If we just considered this to be a cubic equation, the discriminant would be, and again this would depend on the same inputs to G2 and G3, which we'll get back to in a second, omega 1 and omega 2, which define our lattice. This depends on those things, and the discriminant would look like this. G2 cubed minus 27 G3 squared. We'll come right back to that. But for now, I'm going to show you a couple of images that give you a better idea of what these things actually look like. Okay. Since all of this seems to be public info, I don't have a problem doing this. I thought about it. I almost mapped some stuff in Maple. I have the personal license, but it would break my heart if I lost that license for using their stuff in a video. So I'm going to show you what Wolfram has on their page if you look up the Weierstrass elliptic function, so you can kind of get an idea of what's going on. So you can see here they've mapped the real part of the Weierstrass elliptic function, and here these two numbers here, that's G4 and G3. These are those elliptic invariants that we were discussing just a second ago. So they've called G2 4 and G3 0. And as you can see, there are poles here. It looks like there's two of them, and they map right next to each other. And then on every front, here's the real part as some kind of a colored contour-like plot. You can see these red things. Those are the poles. And you can very clearly see the double periodicity of this function. It looks like there's squares, and if you take any point, you look at the next square, or you look one square up, it's going to be the same result. Looks like they've somehow mapped color as maybe a modulus or something like that. Here you see the imaginary part, and you also see the poles. Okay, the poles are different here though. They look like they're kind of slanted a little bit, and I think we'll cover that here in a little bit. Here's P prime. This is the derivative of that Weierstrass function. Another thing to note before we go to P prime is that this is clearly an even function, right? This, if you move over a little bit this way, it's symmetric across, this imaginary, I shouldn't say imaginary, but this invisible axis here, right? Similarly, P prime is odd, okay? Or conversely, I should say, it's odd. You can also see that there's more little red spikes here. This looks like it's got more like a flower that has 6 petals instead of 4, right? That's because this one has that 1 over z cubed, not the 1 over z squared. So it's got an extra order of poles. And here again is its imaginary part. You can see this is odd. If you look at one side versus the other, it's going to be something opposite. And so that's kind of what we're looking at. Again, these are doubly periodic very clearly. These are what these things look like in the real world. One note here, it's clear we can't plot the entire thing. That's why we're just looking at the real and imaginary plots. The reason we can't plot the real thing is because it's a complex function, right? It's going from C to C. So technically, this is a 4-dimensional function. So we're taking individual aspects of it and looking at them in piecewise. Here, we actually see the modulus of the function. This is an interesting one. Again, very obvious double periodicity. Same with this. Here's the modulus of the Weierstrass P prime function, double periodicity. And you could see these poles here are very, very clear. So yeah, we'll get back to the invariance and the discriminant, and I'll talk about the first modular function. Okay, so here's our two invariants, and the discriminant of that differential equation as a cubic. And I want to show you something. This is kind of the idea that leads to these modular functions. Let's say that I scaled omega 1 and omega 2 by some constant lambda. Okay? And let's say I did that for all of these. So I'm just shoving it in here. Hopefully you can kind of see what I'm doing here. What's this going to lead to? Well, here it's going to lead to the same thing I had before, divided by a factor of lambda to the fourth. You see that right there? I probably should connect that. Here, same thing, okay? Except not lambda to the fourth, lambda to the sixth, right? What's this one going to do? Well, it's going to give me from G2 a factor of lambda to the fourth, but then I have to cube that. So it's going to give me a factor of lambda to the 12th in the denominator here. Similarly, factor of lambda to the 6th, I square that, that's lambda to the 12th in the denominator. So I'm going to get delta of the same lattice divided by lambda to the 12th. Now this was, I guess, Klein's big idea. I'm going to write it this way to begin with. What this winds up being is, and I think the more you think about this, the more there's probably plenty of ways to write this, or different modular functions you could come up with. This is the modular function. Now, again, let's just, as a thought experiment, let's see what happens when I plug in lambda, or scale by lambda, okay? So I'm just scaling all these omegas by lambda, and what do I get? Well, I get G2 cubed, omega 1, omega 2, over lambda to the fourth cubed. So that's over lambda to the 12th, okay? And then I get the discriminant of omega 1, omega 2 over lambda to the 12th. But these cancel. So what I really get is my original lattice plugged into J. In other words, I can scale my lattice, my two periods, by any lambda. This works for all lambda in C. And I guess maybe you want to specify that lambda isn't 0. I mean, just so you don't have something stupid. But it works for all lambda in C. And what I've got here is I can scale this lattice by any lambda I want, and I get the same thing. Okay? Another thing to note, you remember how this lattice here, which is determined, the lattice, which is determined by omega 1 and omega 2, how this actually equals another lattice determined by omega 1 prime and omega 2 prime, as long as we have some a, b, c, d integers that map omega 1 and omega 2 to omega 1 prime and omega 2 prime, where a, b, c, d has a determinant of plus or minus 1. You remember that? Well, this actually winds up being part of a very special group. And what I'm about to say may be a little weird, but it turns out you can do some math, and you could take this pair, omega 1, omega 2, and you could just scale it by lambda equals 1 over omega 1, and what you get is 1 omega 2 over omega 1, and we just rename that tau. And what we've specified about tau is that it's not real, okay? So if we look at the complex plane, it's not on this line. It's either up here or it's down here. And we can show that the imaginary part, without losing any generality or anything about the function, has to be greater than 0 pretty easily. So what we can really specify about this is that that tau has to live in what's called the upper half plane, which is just this part of the complex plane. Right? Here's your real line, here's your imaginary axis. It has to have an imaginary part of greater than 0. So it lives in this upper half plane. And what that means is that we can actually orientate these matrices to only have positive determinant. And so we're really just looking for matrices with integer coefficients that give us the determinant of 1. And what we'll see here in a second is that J is actually invariant for all matrices as Möbius transformations that have derivative 1, exactly 1, with integer entries. This winds up being a really special group called PSL2Z. Okay? Any element of this expressed as a Möbius transformation on tau gives us the same thing after we've plugged it into J. So here's an example of that just really quickly, because these things are not super easy to, they're pretty easy to find, the elements of this group. But there's a couple of generators. We'll talk about this way more in depth later on. One of them's S, okay? And it looks like this. You could do this in your head. 0 times 0, 0. Minus 1 times 1, that's 1. So the determinant here is 1. So it's definitely in this group. And if we apply this as a Möbius transformation, and by that I mean A, B, C, D would look like this. A tau plus B over C tau plus D. Then the effect that this is going to have on tau is going to be minus 1 over tau. And what we find is that J of minus 1 over tau just equals J of tau. So this is the first modular function we have. And we don't write it like this. We write it like J of tau. Okay? So I'm just going to erase this, and I'm going to call this is J of tau. This is Klein's modular function. Okay? Notice we're not really talking about elliptic functions anymore. We're kind of more talking about these Eisenstein series and the lattices. But this is really spectacular. I'll take a second to show you what this group means. Okay, so the idea of this group, all right, and you can maybe imagine this Klein modular function kind of mapping between these different sections. This is the upper half plane. There's the real line. I guess tau you would be using, but it doesn't matter. You understand what I'm saying? Here's the complex plane, the upper half plane. You have this first fundamental space, I, okay? And this is where you're not transforming it at all. And then there's these two generating transformations. There's T, which is a translation. It takes this element here and sends it over here, okay? And then there's T inverse, which takes this element here and sends it over here. All it does is move it over by 1, okay? And so you could see that each one of these big, tall spaces is about 1 thick, exactly 1 thick, right? That's the measure of this length, okay? And that actually looks like a 2, and I really don't like that, but I know I said that, but I'm going to just correct it so it doesn't look like a 2. Now somehow they look more like 2s. There you go. Okay, and this is the way that this thing works. T is pretty easy to understand, right? 2t is going to go over here, 3t is going to go over here, right? Blah, 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 blah. But, and maybe I could change the color of this. Did I just change my color? No, I didn't. How do I change my, well, whatever, I don't give a shit. Here's what's happening with S. You're starting with this I, and you're mapping down into this little guy here. Okay, so this part of the imaginary line is being inverted and mapped down here. Okay, so these 2 points are going to be kind of close together, but this point at infinity is going to be mapped all the way down to 0, if that makes sense. Okay, you're inverting it. And the crazy thing is, points on this side are going to get mapped over here, and points on this side are going to get mapped over here. Okay? And if you want to see, obviously this is S here, this region right here, that looks, kind of like a top or something like that. I'm going to color it in here. That's S. And I can translate S. So here I've performed S on I, and then I've translated it 1 over. So I've just taken the point and brought it over here. I've translated it 1 over this way. I've taken the point and I brought it over here. So these are just translations of S. But if you asked yourself, well, what if I went to T first and then performed S? It would just go down here, right? No. It goes over here and then it comes down and across the axis to somewhere over here. So that's the idea, okay? S takes stuff that's over here and sends it over here. All right? And T just translates. Okay? This is the basis for everything, and you'll find later on that that actually all elements of this really special group that we're talking about can be written in words of S's and T's. And S squared is just the identity. So if I went to S and then I went back, I would get this identity again. And that makes a lot of sense, since 1 over minus 1 over minus 1 over x is just x, right? And t can go as many times as you want. So these things wind up looking like st squared, st cubed, st inverse, whatever. You know what I'm saying? You wind up getting words that look like this, that describe these different transformations. These are all part of this group that I'm talking about, is called the modular group. And the transformations that they are associated with are called unimodular transformations. So maybe if you didn't know anything about modular functions before watching this, maybe one of the questions in your mind was, why the hell do they call them modular functions? Well, because they're invariant under transformations that are represented by the modular group. I think that's all I want to say on that, except, oh, maybe one other thing. There's kind of a neat, this is sort of fun to play around with, there's sort of a neat identity or relation in this group, that if you do this 3 times, you get back to identity, which is kind of odd. But if you try this for yourself, right, perform this, I'm sorry, did I do that? I did it, oh my god, I had an extra S, didn't I? I sure did. Start with X, okay, start with X, then add 1, then go minus 1 over that, then add 1, and then go minus 1 over that, and then add 1, and then go minus 1 over that, and you should wind up back at X. All right, take it easy.